Alright, so we're ready to start talking about circuit elements and phasors. So remember, our goal here has been to find the steady state solution. And I'm not going to go through all the details, but remember, we have these ideas now of phasors. And so just to remind you, if we have a voltage that's equal to Vm, remember it's always the cosine function, omega t plus phi. The key thing is that when we did circuit analysis on this and we solved the differential equation, we noticed that the steady state solution had the same frequency, so omega didn't change. The only thing we really needed to keep track of was the amplitude or the magnitude and the phase angle. So this is my phasor, which again, these things you just really should commit to memory here. Vm cosine of phi plus j Vm sine of phi. And that's just, of course, from Euler's identity. Alright, so now we want to start applying this to circuit elements. So we have to first see how circuit elements get these affected. So let's, of course, start with the easiest one here. Let's start with the resistor. And if we go back to our first course in circuit analysis, we have one of the very first equations we learned was that V is equal to I times R. You know, voltage is equal to current times resistance. So that was one of the very first things we learned, of course. And so what we're going to do is we're literally going to do the same thing here, but then what we're going to do is we're just going to do phasor transforms. So if I do a phasor transform here, I would have, well, I'm going to say, first off, I'm going to say V is equal to, I'm going to have some current, Im cosine omega t plus phi times my resistor. Now I'm going to do a phasor transform, so I have my phasor voltage, and then this would just be Im at an angle of phi times my resistance. Now this is just, I want to emphasize, this is just my phasor current. And this right here, of course, is the phasor voltage. So what does that mean we have going here? Well, what that means is we can rewrite this, and what we have is that the phasor voltage is equal to the phasor current times my resistance. And the beautiful thing about this is that this is still just Ohm's law. So for resistive elements, Ohm's law still applies just like we would. Now, I want to emphasize again, these voltages and currents that we're looking at in these equations, these are phasors. So these are both phasors that we're looking at. So those are going to be complex numbers. Because whenever I say a phasor, you should think complex number, because even, I'll go ahead and point back to here, this right here is a complex number. I'm writing it in polar form here, but it's a complex number. So whenever you see phasor or hear phasor, you should think complex number. Alright, so let's move on, and let's talk about what happens with an inductor. Well, now we have to remember the current and voltage relationship for an inductor, and it's that the voltage is equal to my inductance times the derivative of the current. So I'm going to go ahead and start off with a current, and I'm going to take this a couple steps at a time. So I've got a current here that is Im cosine omega t plus phi. But of course, what do I want here is I want the derivative of my current. So I need to find my derivative of my current. So this is just taking a derivative with respect to t. And so this would be just Im times, and then derivative cosine is negative sine omega t plus phi, and then using the chain rule, I would have omega on the outside there. This is equal to it. So let's just clean that up a tiny bit, rewrite some things in order here. So I have my derivative is negative omega Im sine of omega t plus phi. So if we plug that into my equation here, I'd have v is equal to, and I'm going to write this just, I like writing the omega first for some reason, omega L times Im sine omega t plus phi. But now I want to do a phasor transform, because I want to see what happens when I'm in the phasor domain with this. And of course here, the left-hand side is easy. That just becomes my phasor voltage. But we have to look at, before I even do that, we have to remember here that in order to do a phasor transform, I don't want sine functions, I want cosines. So I'm going to rewrite this as V is equal to omega L times Im cosine of omega t plus phi minus 90 degrees. All right, now I'm going to do my phasor transform. So I've got my phasor voltage is equal to omega L times Im at an angle of phi minus 90 degrees. And for those of you paying attention, I've made a mistake here. I'll go back and correct it. What was my mistake? Well, I have negative omega Im and I've dropped my negative. So I need to put a negative back in on all of these here. So I dropped my negative there. Very important. Easy things to miss here if you're not careful. So if you had already caught that, good job. We did go ahead and fix it. All right, so again, this is a phasor. And this here is also a phasor. Okay, so then what do we have here? Well, we have to do a little bit more manipulation here because this isn't a very friendly form for us. And doing a little bit of manipulation, we can rewrite this as V is equal to negative omega L. And then the key thing here is that, remember, one way to write this, my hand hit something there, is Im e to the j times phi minus 90 degrees. Remember, that's another way we can write this here. I don't like that phi there. Let me redraw it. Now, you might say, why am I doing that? Well, I'm trying to simplify this. And when we get to this final answer, it actually will be very simple. But let's see here. We got minus omega L. Then I'm going to have I'm going to do a little bit of, it's not trickery or anything, it's just using properties of exponents, is that, well, if you have things that you're adding together there, you can just multiply. So I have e to the j theta, or j phi, times e to the minus j 90 degrees, and that's going to get me my previous line. Now that's important because I'm going to do a little side computation here, and I'm going to compute here e to the minus j 90 degrees. Because using Euler's identity, this would be cosine of negative 90 degrees plus j sine of negative 90 degrees. But wait, cosine of negative 90 degrees, that'd be 0. And then this would be minus j. So the key thing here is I have minus j now that I can substitute in for this term here. And we'll see why that's important in a second. So what do I wind up with here? V is equal to, well, I've got two negatives here. So I got negative times a negative, so that is positive now. J omega L Im e to the j phi. But I'm just going to rewrite this back in my standard kind of angle form. This is Im at an angle of phi. But let's look at what we got here. So we've got here, this is my phasor voltage. But then here, this is just the phasor current of my original current, I. And I can scroll back up just to show you here. Remember, we started with I is equal to Im cosine omega t plus phi. We took a derivative and did all that work, but then wait, I just have Im times an angle of phi. Now, this has got something really important going on here. Look at j omega L here. These are all numbers that we know. And so really what we wind up with here, and this is the key thing here, I'm going to star this, is we have j omega L times I. So this is a very important thing to notice here. And so we have an Ohm's law. I'll put it in quotes, relationship here. I mean, it's not Ohm's law. Ohm's law deals with resistors, of course. But what do we have here? Well, we've got j omega L, but these are all just numbers. And yeah, that's a complex number here, big deal. Who cares about the fact that it's a complex number? Times phasor currents. So what we've really noticed here is for inductors, we'll be able to use all of our analysis techniques that we learned with resistors here when we're doing steady state. So that's the big deal from here. Now, of course, we have one other circuit element here. The other circuit element we have to look at, of course, is the capacitor. And the capacitor voltage-current relationship is that my current is equal to C times the derivative of the voltage. And so you go through the same argument. I will, walk us through it a tiny bit here. I'm not going to do it all, but you'd start with your voltage is equal to, Vm cosine omega t plus phi. You take your derivative. So taking the derivative, you'd have derivative of the voltage with respect to t would be negative omega Vm sine omega t plus phi, and then we just keep going down the exact same process that we did for the previous thing for the inductor. Now, it is going to be slightly different because what we're going to wind up with here is we're going to wind up with that my phasor current is equal to j omega c times my phasor voltage. And, we have to be careful here. I mean, this is fine. There's nothing wrong here. But this isn't an Ohm's law type relationship yet, because remember, voltage is equal to something times current for an Ohm's law. So what we really want to do is write this as V is equal to 1 over j omega c times, my hand's getting that, times my phasor current. So this is the big deal here. And again, this is an Ohm's law type relation. And now, we're essentially done today, but I want to emphasize what are the three equations we really learned today. Well, these are all phasors, remember. So V is equal to IR, it's still the same. Then for an inductor, it's V is equal to j omega L times my current. And then for a capacitor, it's V is equal to 1 over j omega c times my current, which another way to write that one, and you'll see us doing this frequently, is pulling that negative, making it negative j over omega c, because you can pull a j up into the numerator just by making it negative. And so these are my Ohm's law types of relationships, and actually this is where we're going to pick up on the next video.